We're going to finish up lecture note 7 now, model selection for multiple regression. So now we're really going to get into how to select models, how to think about what are the most appropriate variables to include in your model. What are you interested in? So the first question you should be asking yourself when you sit down to run a regression is what's your goal? There's two main goals that we might consider. The first is unbiased estimates of a particular coefficient or arguments for causality. The second is prediction. Maybe we want to use regression to predict out of sample. We want to predict future stock values or future commodity prices, etc. So in that case, our goal might be to maximize the R-squared or other measures of model fit. For this class, our primary goal is number one, an unbiased estimate of a particular coefficient. Usually, the example we've been working with is unbiased estimates of student-teacher ratios on test scores, holding other variables constant. So what's our approach to model selection? We want to specify a base model, what you think is correct. So in the test scores and student-teacher ratios example, we've been specifying our base model as just test scores on student-teacher ratios with no other variables in the model. We want to specify a range of plausible alternative models, and that would be add or subtract additional variables, different functional forms like adding squared terms or adding interactions between two variables. You want to compare your different models. So once you've specified your base model and a few other models, you run them all and then compare the outputs. Do ask yourself questions like, do additional variables substantially change the coefficient of interest? So do the additional variables substantially change the coefficient on student-teacher ratios? If so, why? Maybe there's omitted variable bias that we have to be concerned about. Is the additional variable statistically significant? If it's not, then maybe you don't need it in the model. If it is, then that probably means it's an important predictor of the dependent variable. It's important to not simply try and maximize the R-squared. So don't just throw in whatever you can to maximize the R-squared. That's not the most appropriate model necessarily. So also don't run a kitchen sink regression. That means take all the data that you have and run a model with every single variable that you can possibly put in the model. You know, if you have the test scores of school districts, maybe it's not important to put in the number of dogs within every school district or something like that, even if you have data on it. So don't just run a kitchen sink regression and then drop all the coefficients or all the variables with insignificant coefficients. You have to think about what you're putting in the model. So think about what variables make sense. So every variable you add to the model, think about why you're adding it to the model. What do you think is going to happen when you add it to the model? What sign is the coefficient going to have? Is it going to be negative or positive? Do you think, in other words, do you think that variable is going to have an increase in that variable is going to have a positive or negative effect on the dependent variable? How do you think that the inclusion of that variable is going to affect your coefficient of interest, the coefficient on student-teacher ratios? So basically you have to think about what you're doing. Imagine if your boss told you to find out this relationship and you said you just ran everything you could think of without actually thinking about why you're running it, then that's not a very good job. You want to be able to justify what you're doing. So some common steps. Look at your data. We've done this already. We want to look at summary statistics like the mean and the standard deviation, the minimum and the maximum. So you want to look for outliers. If we have student-teacher ratios and that's our x variable, and we find that there's just a class size of 1,000, but every other class is around 22 to 30 or so, you know there's something going on with that data points. Maybe you want to throw that out unless you know for certain that one district has an average class size of 1,000 students, which seems fairly unlikely. Also, if you have percentages, you want to make sure that you have all your percentages between 0 and 1, or maybe between 0 and 100 if it's in, depending on how it's specified. So things like that. You just want to look at your data and make sure it makes sense. Also, we can look at graphs. You can take the dependent variable and graph it against all of the independent variables of interest. That can give you a sense of how correlated they are and also what the expected sign of the coefficient should be. We'll look at an example of that in a moment. And then estimate the baseline model and the alternative models and make comparisons using things like the F statistic that we just learned. Okay, just a little side note of caution about the R-squared, or adjusted R-squared. A high adjusted R-squared means the regressors explain the variation in Y. They explain a high percentage of the variation in Y. That's all it means. It doesn't imply that you have a eliminated omitted variable bias or you have causal effects. It doesn't imply that you have unbiased estimates of your coefficients. A higher squared does not mean anything, or does not imply anything about statistical significance of the coefficients. It does not mean you have an appropriate set of regressors either. So now let's put this into practice. We said the first step is to look at your data. Look at the summary statistics or graph your data. So we're going to take the example from the book, Test Scores and Student-Teacher Ratios. And so these graphs you're seeing are coming straight out of the book. They've plotted for us test scores and the percent of English language learners. That's panel A up here. They've plotted test scores and the percentage of students in the district qualifying for a reduced price lunch. So that's going to be an indicator for essentially the average income in the district. And then they have test scores plotted against the percentage of students qualifying for income assistance. So the variable that we have seen so far is this percent English language learners. They're now adding reduced percent on reduced price lunch and percent qualifying for income assistance. So a couple of things we can learn from these graphs. Each of them is negatively correlated with test scores. They're all downward sloping. If we were to draw a line of best fit for each of these graphs, those lines would all be sloping downward. And that kind of makes sense. The percent of English language learners we talked about, as that goes up, we're going to see test scores go down because students that are simultaneously learning English and some other topic are going to have a harder time in that other topic. And then also the percent qualifying for reduced price lunch, that's going to be again an indicator for income. It's fairly well known that parents with higher incomes can spend more time with their children, teaching them to read, teaching them to or helping them with their homework, etc. So parents that don't have a high income, maybe they're working more than one job, they're working longer hours, they're working at night, so they don't get to spend as much time with their children and help them with their homework, etc. So we're going to see a downward sloping relationship here. The test scores go down as incomes go down. Now, the percentage qualifying for income assistance, that's going to capture basically the same thing. It's also downward sloping, and we'll see when we look at the regression outputs, those two variables are fairly collinear. So remember, in our assumptions for multiple regression, we need variables that are not highly collinear, and it's called multi-collinearity. If we have two variables that are highly collinear, like B and C here, then one of them is going to soak up the variation in the other. The second step was to estimate a baseline model, and the baseline model is going to be test scores on student-teacher ratios. Our variable of interest, again, is student-teacher ratios. So we're going to estimate, or the book estimates the first model here, test scores on student-teacher ratios. Then they're going to add a couple of additional variables. In the second column in the next table I'll show you, they're going to add the percent of English as a second language students. That's English language learners here. And then they're going to add percent ESL and percent lunch. That's this one and this one. And then they're going to add all three. They're going to add the percent ESL, percent lunch, and percent income assistance. So they're going to, here's our baseline model. Our coefficient of interest is beta 1 on all of these models. We want to see what happens to beta 1 as we introduce the additional variables. So this is how you would see regression results typically presented in an economics paper or any academic paper really. You're going to see them in a table, and so you can see how adding additional variables affects your variable of interest. Our variable of interest is student-teacher ratio. So beta 1 in each of those models is this top row here. So this first column is this regression equation, test scores on student-teacher ratios. You can see that percent English learners is blank, percent eligible for subsidized lunch is blank, and percent on public income assistance is blank. That means that they weren't included in the model. The only variable in the model in column 1 is student-teacher ratios. And we have the standard error of regression at the bottom, the adjusted R-squared, and the number of observations. Importantly, the number of observations stays the same across all regressions, meaning that whatever difference we see in these coefficients across regressions is not due to a change in the number of observations. Okay, so we have this model we've seen a bunch of times now, student-teacher ratios and test scores. The coefficient on student-teacher ratios is negative 2.28, meaning that a 1 unit increase in class sizes decreases average test scores by 2.28 points. So now let's look at what happens when we add percent English learners to the regression, column 2. That's this regression here. It's test scores regressed on student-teacher ratios and percent ESL. So first thing first, let's look at what we expect that coefficient to look like. Is it going to be positive or negative? Well, we expect it to be negative. It should be a negative coefficient, and indeed it is. So the coefficient on percent English learners is 0.65. So that's a 1 percentage point increase in percent English learners reduces test scores by 0.65 units of test scores. Now, important, we're not so interested in this variable for this analysis. Again, our variable of interest is student-teacher ratios. So we want to find out how adding percent English learners to the model affects student-teacher ratio. And at the beginning of lecture note 7, we discussed how percent English learners is going to be an omitted variable that could cause bias. And indeed it does. It reduces the magnitude of this coefficient by roughly, it cuts it in half. It goes from 2 to 1. So this variable, percent English learners, appears to be pretty important, at least for addressing omitted variable bias in student-teacher ratios. What about the R-squared? What can we learn from that? So the R-squared, remember in column 1 here, is only roughly 5%, meaning that student-teacher ratios only predicts about 5% of the variation in test scores. But the addition of percent English learners predicts roughly 42%. So the combination of these two variables predicts about 42% of the variation in test scores, which is, it's fairly large, or a fairly large jump. Okay, so we've added percent English learners. Now let's look at adding some additional variables. Let's add the percent on percent qualifying for reduced price lunch. Column 3 here. We would expect that the coefficient's going to be negative because we plotted the two variables, test scores and percent eligible for subsidized lunch, and then it looks like the correlation is negative. So indeed we find that the variable is, or the coefficient is negative, which is what we expect. How does it affect student-teacher ratios, the coefficient on student-teacher ratios? Well, it drops a little more. It goes from negative 1.1 to 1, but that's not nearly the drop that we had when we went from 2.28 to 1.1. So that suggests that percent eligible for subsidized lunch is perhaps an omitted variable that's causing a little bit of bias even after controlling for percent English learners, but it's not nearly what it's not nearly the bias that percent English learners is capturing. So that's good. We can see that after we have controlled for percent English learners, that coefficient on student-teacher ratios is going to remain fairly stable. It doesn't change much. Hovers around negative 1.1, which means that we've at least addressed a good portion of the omitted variable bias with just percent English learners. What else can we learn from this? The R squared continues to go up after we've added a third variable, and that's to be expected. You add another variable that explains variation in test scores, the R squared is going to go up. One other thing to note, the stars, I haven't mentioned this before, but the stars represent levels of significance or confidence. So if we have 2 stars, then we have 99% confidence, or our significance level is 1%. We're rejecting a null hypothesis that these variables or these coefficients are equal to 0 with 99% confidence. If we have 1 star, then we have 95% confidence, or 5% significance level. So each time you see 1 star, you know that you can reject a null with 95% confidence, the null that the coefficient's equal to 0. If you see 2 stars, you know you can reject that null with 99% confidence. Okay, so let's now look at adding percent qualifying for income assistance to the model. So we're going to remove percent eligible for subsidized lunch and add instead percent on public income assistance. Okay, in this case, the coefficient on student-teacher ratio goes up a bit, but not nearly. It doesn't rebound back to negative 2.28 or anything, so I wouldn't worry too much about that. And I would actually say that that coefficient, or the student-teacher ratio coefficient, is robust to the addition of percent subsidized lunch or income assistance after we've controlled for percent English language learners. So it doesn't really matter what variable we're going to include. Percent on public income assistance also has a negative relationship with test scores, as we would have expected from the scatter plot above. The R squared goes down a bit relative to column 3, but we're not really concerned with maximizing R squared, so it's better to think about which of these variables is more important. Which one do we think is a better explainer of test scores? And one thing to note is that the coefficient on public income assistance is more statistically significant than the coefficient on percent eligible for subsidized lunch, but the R squared is higher in column 3 than it is in column 4. So it's hard to choose. Another way to think maybe to choose would be to look at the coefficient on student-teacher ratios, the coefficient of interest. If we want to be as conservative as possible, maybe we're going to pick column 3 because over column 4 because this suggests a smaller effective class sizes, and we're getting a more precise estimate. We're 99% confident relative to 95% confidence here. All right, what if we include both? So we already said that percent ESL, or sorry, percent lunch and percent income are going to be highly correlated, leading to some imperfect multicollinearity. So let's see what happens when we add both of them to the model. All right, our student-teacher ratio coefficient stays about the same. We lose a little bit of statistical significance relative to column 3. Percent English learners stays about the same relative to column 3. Percent eligible for subsidized lunch is basically unchanged. What does change, though, is that percent on public income assistance is now positive and statistically insignificant. So we knew that it would become statistically or at least the significance would decline because these two variables are highly correlated, and controlling for one or have both of them in the model means that we're essentially controlling for all the variation in income assistance when we have subsidized lunch in the model. And so only one of them is going to be able to matter here. So column 5 basically suggests that we should pick between the two. We should go back to column 3 and 4, and we should pick between having percent eligible for subsidized lunch or percent on public income assistance. I'd probably go with column 3 just because that's a bit more conservative of an estimate on our student-teacher ratio. Finally, we can do this in our own data. We can estimate several different models using the beer data from problem set 4. Maybe what we're mainly interested in is kind of getting an elasticity estimate. Now, this is not an elasticity because these variables are not logged, but here we are regressing the quantity of beer on the price of beer, and then we're going to start to include more variables as we go down in model complexity. So let's look at how the price of beer affects the quantity of beer consumed. So I'm going to estimate the first model, summarize it. We get a coefficient of negative 9.835, and it's statistically significant, t-value of negative 7. All right, so maybe I think that the price of liquor is an important omitted variable. I should add that to the model. So let's do that. Maybe I think that the price of liquor is correlated with the price of beer. It's also going to be correlated with the quantity of beer consumed. Maybe there's substitutes. The price of liquor goes up, people are going to consume more beer, or the price of liquor goes down, people are going to consume less beer. So let's see how this works. Estimate model 2. Interestingly, this actually, so our coefficient on the price of liquor is statistically insignificant, a t-value of 0.659, meaning that it doesn't really have a substantial effect on the quantity of beer consumed, at least in this data set. Granted, we only have 30 observations, so it's not the greatest of data sets. But adding this variable to the model actually increased the price of beer. So if I was just to compare these two models, I'd probably go with model 1, just having the price of beer in the model. How about adding, maybe I think that income is an important predictor of how much beer people are consuming. So let's throw that in the model and see what happens. Estimating model 3. All right. Now we've gone from a coefficient of, what did we have up here? Of negative 9. Now our coefficient's negative 2.5 e to the 1, so that's going to be negative 25. So income has a large effect on the coefficient of the price of beer. Income itself also has a large effect on the quantity of beer consumed, so this is an important variable to include in the model. Our R squared is also going up. So we went from 0.63 or 64 to 0.75. Now let's see if the price of other goods has an effect. So the price of beer is negative 2.374 in this one, and negative 2.579 in this one. So that doesn't have much of an effect. So we could include it or not. If the price of beer is our coefficient of interest, we can say it's robust to the inclusion of the price of other goods in the model, so long as we're controlling for income as well.